Okay. Welcome to the second lecture of the course Computer Organization and Architecture. So in the last lecture, we have discussed the introduction for this course. We have defined what is a digital computer. We have discussed different types of computer. We have understood the functional units of a computer, and we have discussed how connection between processor and the memory happens through various functional units like memory address register, memory data registers, instruction register, program counter, and control unit. All these things we have discussed in the last lecture. So in this lecture, we'll be discussing about bus structures and system software. So let us start with the bus structure. Okay. So what is a bus? A bus is a communication channel between any two functional units of a computer. So what is a functional unit? The functional unit, the typical examples for functional units are processor, memory, secondary storage devices, or any IO devices. So whenever there is a need to transfer data from the processor to memory, or from memory to the processor, or from memory to hard disk, or from hard disk to memory, or from memory to a printer, okay, or from keyboard to a printer, all this communication happens through a particular electronic circuit, and that electronic unit is called as bus. Okay. And in a typical computer should be able to handle one word of data. Okay, in a typical computer, all units, all here units in the sense it refers to the functional units like processor, memory, secondary storage devices, or any other IO devices should be able to handle one word of data at a given time. Okay, so that the data can be transmitted at a reasonable speed, right? So what is meant by a word? So we have already discussed in the previous one of the previous class. So there is no fixed size for the word. The word size varies from computers to computers. So in some computers, the word size may be 32 bits. In some computers, the word size may be 32 bits. Okay. In some other computer, the word size may be 64 bits. In some other computers, the word size may be 64 bits. Okay. So it depends. It depends on the type of the computer. Depending on the type of the computer, the size of the word will change. Okay. So when we say that a computer is a 32-bit computer and when we say it's a 64-bit computer, so if the bus size is, so if the, what is bus? Already we have discussed, bus is a communication channel. So if the bus size is 32 bits, then we say that that is a 32-bit computer. That is in this computer, the bus has 32 lines, okay, or there is 32 lines or 32 wires for communication. So using this computer, 32 bits of data can be transferred simultaneously. Okay. If the bus size is 64 bit, that means there will be 64 lines. It means there will be 64 lines. So in that case, we call that computer as a 64-bit computer. Okay. Okay. So depending on the bus size only, the uh, depending on the bus size only, we call whether a computer is a 32-bit or a 64-bit computer, and whether if it, and also depending on that only we fix the word size. If the bus size is 32-bit, then the word size also will be 32-bit. If the bus size is 64-bit, then the word size also will be 64-bit. Okay. So let us assume that so here what we are saying in the sense, all units of the computer, all functional units of the computer should be able to handle one word of data at a time. So if the computer is a 32-bit computer, then all units should be able to handle or manipulate one word at a time. That is, it should be able to handle, if it is a 32-bit computer, it should be able to handle 32 bits of data at a time. If it is a 64-bit computer, it should be able to handle 64 bits of data at a time. Because the bus size is 64-bit, then if the functional unit is also able to handle that much amount of data at a time, then 64-bit data can be transferred through that bus immediately. Okay, so that is the reason we say that the functional unit should be able to handle one word of data at a given time to achieve a reasonable speed. Okay, so let us assume there is a processor here. Say this is a processor. Okay, say there is a memory unit here. This is a memory unit. Okay, say the processor and memory unit are connected through a bus. This is the bus. Okay, through this bus, right? Now what does it mean that it is a, so if it is a 64-bit computer, this bus internally, if you see, there will be 64 lines or 64 wires will be there. Small wires. Okay. So here also 64 wires will be there, right? Here also 64 wires will be there. So it means that this processor can send 64 bit of data to memory at a given time. Similarly, memory can also send 64 bit of information to the processor at a given time. So this 64 bit is called as the word size. So like that, all functional units, maybe somewhere here hard disk will be there. So hard disk also should be able to handle 64 bit of data at a time. Maybe somewhere else printer will be there. So the printer also should be able to handle 64 bit of data at a time. Okay, that is should be able to handle one word of data at a time. Here, as it is a, as the bus has 64 lines, we say it is a the word size is 64 bit. Okay, I think the point is clear, right? So this is how we define bus. Bus is a group of lines that serves as a connecting path for several devices. Devices includes processor, memory, secondary storage devices, and any other IO devices. Okay. So the bus, what are the different types of lines or the wires the bus contains? So the bus basically contains three types of lines. These are address lines, data lines, and control lines. Okay. So it is not that the bus is used only to transfer data. No, the bus contains three types of lines. It has address line, a data line, and control line. Okay. Okay, so so the size again, no, the size may vary. Okay, for example, your data line may have 64 bits. In the bus, the data line may have 64 bits. That doesn't mean that the address lines also should be 64 bit. No, the size of the address line, the size of the size of the address lines, it depends on the memory size of the system. Okay, or how much maximum memory it should support, it is based on that. Okay, if the address line is 20 bits, if the address has only 20 lines, okay, if the address uh, the address lines of the bus has only 20 lines, means then it means that this bus can maximum address only 2 to the power 20 locations. Okay, it cannot support anything beyond that. That is, then there is a restriction on your memory. Then your memory capacity cannot beyond the system's memory capacity cannot go beyond 2 to the power 20. Okay, because you may install a high size memory, uh, but you don't have sufficient bus size to do that. Okay, so 2 to the power 20 means which is equal to this much. So it can address this many bytes. Okay, 1048 comma 576 bytes. Okay, it can address this much bytes, right? So so uh, the address line, so the point is, it is not necessary that the address line should be same as the data lines. Okay, so data line represents how much bits of data can be transferred in a given time. Okay, based on the size of the data lines only, we say whether it is a 32-bit word size or a 64-bit word size, or a 32-bit computer or a 64-bit computer. But address lines, again, it may vary. Okay, and then control signals will be it may not have this many lines. It may have hardly 4 or 5 lines. Okay, the typical two control signals are read and write. Okay, the typical two control signals are read and write, which are the commonly used control signal. There may be other signals depending on the type of the device which are involved in communication. Okay, and some of the signal may be reserved. Okay, so control signal typically will not take more lines, right? So the point is the bus contains three types of lines: address line, data lines, and control lines. Address lines are used to refer the particular memory location, and data lines are used to transfer data from one device to another device, and control signals tell what is the operation to be performed, like whether read or write operation, and also it may generate the timing signal, like at which time the task should be done. Okay, fine. The simplest way to interconnect all the devices in a computer is to use a single bus. So a typical computer, like a personal computer that we are using, they will have only one bus. That is the simplest way to interconnect the all the devices of a computer. But a more sophisticated computer may have more than one bus. Okay, we'll come to that. So if there is only single bus, there is only one bus. Okay, then only two units can use the bus at a given time. More than two units cannot use. Okay, then only two units can use the bus at a given time. And control lines are used to arbitrate multiple requests for the use of the bus. So this is another job of the control lines. Say for example, uh, we have a bus, something like this. Sorry. Say we have a bus. Okay. Say say here is the processor. Here is the processor which is connected to the bus. Okay. And here is the memory which is connected to the bus. Okay. And here is the hard disk which is connected to the bus. Okay, and like that maybe another devices, say there is a keyboard which is connected to the bus, right? So there is only one bus. You see, there is only one bus. There are not different buses. There is only, this is the one primary bus. Through to this bus all the devices were connected. Okay, so now say that uh, for example the hard disk says that it want to use the bus at time t naught. Okay, and say that memory also want to use the bus at the same time t naught. Okay, so memory also want to use the bus at the same time t naught. So hard disk say that hard disk want to write something to memory, right? The control unit in the hard disk, it gives a signal that some data should be written to the memory, and memory want to send some data to the processor. Okay, so that is processor has requested some data previously, and that should be transferred to the memory, and that will be done by the memory controller. Okay, so now hard disk is also placing a request for the bus, and the memory is also placing a request for the bus. Now who will get the bus? Who should be given the bus? This decision will be taken by the control unit. Not control unit, control lines. Okay, sorry, it's not control unit. This decision will be taken by the control lines uh, of the bus. Okay, the request will go to the control lines. So the control lines will decide like who should get the bus and who should wait, because there is only one bus, so only one device can use the bus. Okay, one device in the sense two device. If memory want to send data to the processor, then memory and processor can use. Okay, if hard disk want to send processor to memory, then only hard disk and memory can use. No, then memory and processor cannot use. Right? So it will be the decision of the control lines to decide like who should be given the bus and who should be asked to wait. So that is the job of the control lines. So this is the typical example of a single bus architecture, single bus structure. You can see there is only one bus, and to that all devices are connected. The input devices, output device, memory, and processor. So input device, you can see that there is only one way communication. It can only send data to the bus. It cannot receive anything. For example, from keyboard, you can only send data. The keyboard cannot receive. From mouse also you can only send signals. It cannot receive anything. Okay, similarly output device like monitor or printer, it can only receive data. It cannot send back anything to the bus. Okay, like monitor or printer. Memory, if you see, it's a two-way communication. It may send something to the bus that should be returned to the processor, or that should be returned to the output device or any other IO devices. So this is one-way communication. And somebody may send the data through the bus to the memory. So that also should be received by the memory. So it's a two-way communication. Similarly, processor also has a two-way communication. Processor may send some information which should be returned into memory, or which should be directly go to some output device. Similarly, processor, some data may be moved from memory to the processor. Okay, so it's a two-way bus. Okay, so in a typical computer, we'll have only a single bus, and it's a very simple bus structure. Okay, and the single bus structure cost low, and also we have the flexibility of attaching peripheral devices, because all peripheral devices should be attached only to the same bus. Only the control lines will decide like who will get access to the bus at a given time. If there are multiple buses available, then there will be more concurrency. Two or more transfers can happen at the same time. If there is a single bus, then only one transfer can happen at a time. Either you transfer between memory and IO device, or between memory or processor, or any one transfer. But if you have more bus, say you have another bus, okay, say you have another bus parallelly, and all the devices are connected to this bus also. Say processor is connected to this bus also, memory is also connected to this bus. Okay, say these IO devices are also connected to this bus. Now what happens? Now what happens if the first bus is busy? Then somebody can use the second bus. Are you getting? Say the first bus is being used between memory and processor, or say memory and what do you call, uh, output device or any IO device. Maybe processor can use the second bus to receive data from the keyboard. Okay, right? Or or processor can, so so normally processor will not receive data directly from the keyboard, but just or processor uh, may communicate with the memory itself through the another bus. Okay, so like that, if there are more than one buses, then two or more data transfer can happen at the same time. Okay. Now here there is another challenge. The challenge is the devices that are connected to the bus. The devices that are connected to the bus, they vary in speed. The speed of all these devices were not same. Different devices, they operate at different speed. So how could we overcome this problem? Why it is first of all a problem? The problem is, see, in a typical system, if you see, the keyboards, printers, they are relatively very slow. They work at a very slower speed. The devices like magnetic discs and optical discs are comparatively faster when compared with keyboard and printers. Or if you consider memory and processor, they are the fastest parts of a typical PC. Okay. Now the processor will be working at a very faster speed, and it will be sending data to some output device, say the printer. But the printer will not be able to accept the data at that rate. Then what happens? The because of the limitation of the printer, then the processor speed also should may be reduced. Are you getting? Because processor may be say sending say 1,000 characters at a time to print. 1,000 characters per milliseconds it is sending to print. But say that the printer can accept only 10 characters per millisecond. Then what will happen, for after sending 1,000 characters, then the processor has to wait for some time, so that the printer can print the 1,000 characters. Then only it can send the next 1,000 characters. Okay, now the speed of the processor is getting limited because of the reduced speed of the printer, right? So such problems will arise. Similarly, say for example, the keyboard can send only say 5 characters per millisecond. 5 characters per millisecond. but say that memory can accept 500 characters per millisecond. Okay, now even though memory can receive 500 characters per millisecond, but the keyboard is sending only 5 characters per millisecond. Again, because of that, uh, the performance of the memory may be affected, right? So as different devices are using the same bus, this kind of problem may occur. So how can we overcome this problem? So so typically this is a very common problem in any computer. Okay, as devices operating at a different speed, they communicate. So there should be some mechanism to smooth out the difference in timing, so that the high speed devices, the what do you call the high speed devices are effectively utilized. For that, what we use is called as buffers. For that, we use something called as buffers, or it is also called as buffer registers, or it is called as buffer registers. So typically, the uh, the, the IO devices will be slower. Okay, so in any IO devices, if you see, there will be buffers. Okay, so for example, if you take a printer, there will be a print buffer. In a printer, say, I'm sorry. So if you take a printer, in a printer, there will be a print buffer. Say there is a printer. So this is a printer. So as a part of the printer, there will be something called as a print buffer. Okay, this print buffer, the size of the print buffer may be less. Buffer is something like a storage. Okay, it's also an electronic storage. Okay, and say that CPU wants to print something. Now we know that processor is a device which is working at a very faster speed, whereas printer is a very slow device. So the so so if the CPU uh, is 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 sending the job to the printer and it is waiting, then it will take a lot of time. Okay, so in between we keep this buffer. So whatever the CPU want to print, it will just write into the buffer. Okay, as the buffer is a high speed device, high speed electronic device, CPU can write into the buffer at a faster speed. After writing the content to the buffer, CPU will do some other job, because maybe some other process may be waiting. So CPU will context switch there. Okay, now the printer will slowly take the data from the printer at its own speed and it will print. Okay, and during this time, when the printer is taking data from the buffer and while it is printing, during that time printer will not be available for other devices, right? So this is how the buffers solves the problem of mm, different devices with different speeds. Okay, similarly, if you take a keyboard, in keyboard also there will be a buffer. Okay, in keyboard also there will be a buffer. So user may be typing key type what you call user may be typing the keys at his own rate. It depends. Okay, different, some users may type fastly, some users may type slowly, or whatever it may be. So the data, whatever the user types, it will not directly go to the memory, rather it will go into the buffer. So this is a buffer. So the first the data will go into the buffer, and this buffer is a high speed electronic device. Okay, this buffer is a high speed electronic device, and from this buffer the data will be moved to the main memory at a faster rate. So uh, so 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 you can say that there will be always some data available in the memory, in the buffer, for the memory to access, right? So this is how the buffer registers are used to ensure that the data transfer happens quickly. Okay, fine. So okay, so in the printer example, whatever we have discussed, so that's what being explained here. Say that you want to transfer some encoded character from a processor to a character printer. Processor sends the character over the bus to the printer buffer, right? As the buffer is electronic register, the transfer can happen at a faster speed. After transferring, the bus and the processor will be released. No more the bus and the processor will be assigned with the printer, because there is no job for the there is nothing for the printer to do with the bus and the processor. the bus and the processor will be released. Bus can be used by any other devices, and the processor, if it has some other task to do, it will do that particular task. And the printer will take the data from the registers at its own pace, and it will start printing the data. Fine. So this is how the typical bus structures works in a normal